In this session, now we are going to see for the next numerical for the buckling analysis. So we can see in this particular determine critical buckling load of a axially loaded long slender bar of length L, which is having a hinged end. The bar has the cross-sectional height h and area A. So we are having an A value, h value. On that basis we can calculate for an I value, AH square by 12. So we are having an cross-sectional area, height and its moment of inertia. Now we need to go for the analysis of this particular beam with respect to the buckling calculations. So the total length of this particular beam is given as a 200 inches. We can consider this particular beam as a symmetry about its x-axis. So we are going to model for the upper half only, that too only a L by 2. Then the boundary conditions become free fixed for the half symmetry model. The total 10 number of master degrees of freedom we need to define along x direction, which will characterize the buckling mode. So it's most important case how to go for the buckling analysis with the help of a modal analysis we are going to see. So start in a sequence, first from a preferences up to the modeling of this particular numerical. So let us click over here, say set our preferences. In the preferences we are supposed to set for structure and just say OK. Once we are setting our preferences, now we need to set for our preprocessor. Let us single click over here. Now set for the element type. Again, this is a particularly beam numerical for the buckling analysis we can see over here. So we are going to use for the beam 3 as a element type. So let us click over here, say add, and now we supposed to add for beam 3 and just say OK. So we are having a beam 3 over here and just close it. Once we are adding our element type, now we need to go for the real constant related to that particular element type. So let us click over here, say real constants, add, again say add and say OK. In that ways we are having 3 unknowns for this particular real constant. So we need to enter for cross-sectional area, moment of inertia and total height of that particularly. So area value 0.25, height value 0.5. So area is 0.25 and height is given as a 0.5. On the basis of these two we can calculate the area moment of inertia of that particular bar, and after calculation we can see I is equal to A square by 12. So we are going to define it 0.0052083. So we need to enter for that one 0.0052083 and then say OK. Once we are sending over here as a real constant sets, just close this pop-up window. Now we need to go for the material properties. So material properties, material models, say structural, linear, elastic, isotropic. Over here we are having a Young's modulus value mentioned as 30E6 psi. So we need to enter for 30E6. With respect to the Poisson's ratio value 0.3. Now we are knowing that this particular numerical is supposed to go for the modal analysis with respect to the master degree of freedom. So we must enter the density of that particular numerical, because without any kind of a density value or external mass we are not supposed to go for the modal analysis. So we need to go for a density value. So come out of these particularly and let us double click over here on a density icon. Say density, I am entering the density for this particularly 0.4 times 0.728 and just say OK. We need to enter for density value and a linear isotropic properties as Young's modulus and a Poisson's ratio. Once we are defining our material behavior, just come out of that particularly. Now we need to go for a modeling of this particular beam. So we are knowing this is total length is given over here as a 200 inches. But we are going to consider this particular beam axisymmetric about this particular x-axis. So we are supposed to calculate only for half of the. So total length is 100. We are going to consider it as an axisymmetric. So in the modeling, say create key points first. key point in active coordinate system. First we are keeping it over here as a 0, 0. Next is axisymmetric, so instead of 200 we are keeping it 100, half of that one, and just say OK. We are having a point placed over here. Now just say line, a straight line in between these two key points. Once we are creating for a point and a line, that means we are having a geometrical entity. So now we need to go for finite element modeling of that particularly. So come out of your modeling and just say meshing. Let us single click over here and say mesh tool. Now we need to mesh this particular geometry, and we can see finite element representative model given over here with the numerical. So say we are having a 10 number of elements along L by 2 length. So we are creating L by 2 as 100. Now we need to go for 10 nodes, 10 elements along with a element 11 over here as a nodes. So set our size control over here and just say 10 in the number of divisions. We need to divide this particular line into 10 number of divisions and just say OK. Once we are setting our global, now we should say mesh, select that particular line and just say OK. Once we are setting, we are getting a finite elements over here. We can cross check over here, just go over here, say plot control, numbering, switch on for the element numbers and just say OK. We can see we are having a 10 number of elements plotted across this particular line. So once our finite elements are created, now we should come out of our preprocessor and we should enter over here in a solution option. So let us single click over here on a solution. Once we are entering in a solution, now we need to define our analysis type first. So we are knowing the procedure for eigenbuckling calculations. So analysis type, new analysis. At the start we need to go for static calculations only. Say static. Now we need to go for the pre-stress effects of that particularly. So say an average menu, because we must know an analysis options highlighted over here. So we are having solution control. We need again one additional option. So say an average menu. Just click over there. We can see an analysis option highlighted over here. So let us single click on this particularly and switch on for a pre-stress effects over here. Just click it on over here and just say OK. Once we are switching on for the pre-stress effects, now we should define our loads. Let us say define, apply, structural displacement. We are knowing we are modeling it for an axisymmetry. That means we need to lock all the degrees of freedom over here at the base node. So say on the nodes, displacement over here on the node, and lock all the degrees of freedom for this particular beam free element and just say OK. Once we are locking the degrees of freedom, now we need to go for the external load. Say force. It's an eigenbuckling calculation, so we are knowing force value stands 1 lb. So we need to enter that particularly. Say on first number node over here, just say OK. Y directional -1, -1, and just say OK, because we can see in the numerical sketch representation our force is acting vertically downward along the y-axis over here. So in that ways we need to enter our external input. Once we are entering for all the inputs related to the geometry, material properties and loading, now we need to solve this particular numerical. Just say solve for the current load step. Let us single click over here, close our status and say OK. Once we are saying OK, now we are having one note highlighted over here that our solution is done. So close it. Now we are going to continue this particular numerical in the next session.